All right, let's dive right into this stress-free toolkit for Chapter 8. If you've ever stared at a page absolutely covered in intersecting lines and felt that wave of math anxiety wash over you, just take a breath. I'm acting as your friendly teacher today to walk you through mastering lines and angles. By the time we finish this explainer, you're going to see the hidden geometry in literally everything around you, and the math is going to make perfect sense.
Here is our roadmap. We are following the exact textbook order, so you know exactly where we are every step of the way. We'll kick things off with basics and constructions, move right into intersecting lines, dive deep into parallel lines and transversals, and finally wrap the whole thing up with a summary and some killer exam tips.
All right, Part 1, Basics and Geometrical Constructions. We're going to start right at the foundation, looking at basic lines and exactly how to build them perfectly from scratch. You know, what's genuinely funny about the word congruency is how simple the concept actually is. In mathematics, we absolutely love using big, intimidating vocabulary, but congruency literally just means things are identical. That's it. If you have congruent line segments, they are exactly the same length. If you have congruent angles, they open up to the exact same degree. They are just perfect geometrical twins. And hey, before you even calculate a single thing, you can actually estimate lengths using stuff sitting right there on your desk. Take a standard eraser, for example. It's usually about 4 centimeters long. You can mentally stack that eraser next to a line segment on your page. If the line looks to be about 2.5 times the length of your eraser, boom, you instantly know the total length is roughly 10 centimeters. No ruler required. It's a fantastic real-world trick.
Now, I highly recommend locking these magic numbers into your brain because they are literally the secret keys to solving almost every exam question in this chapter. A straight line, which gives you supplementary angles, will always sum to 180 degrees. A right angle, or complementary angles, they hit exactly 90 degrees. A whole turn, also called conjugate angles, is a full circle summing to 360 degrees. And a reflex angle, that's just any wide angle sitting somewhere in that gap between 180 and 360 degrees.
Let's actually put this to the test and tackle a complex problem step by step to find angles P, Q, R, and S using those exact magic numbers. Okay, so if P and 54 degrees are complementary, we know they have to equal 90, which means P is exactly 36 degrees. Simple enough, right? Then, if P and Q are supplementary, they add up to 180. Since we just figured out P is 36, Q has to be 144 degrees. Now, if R is conjugate to 260 degrees, they total 360, leaving R at exactly 100 degrees. Finally, for a whole turn summing to 360, we just add up all our knowns, 100, 144, 36, and 54, which leaves exactly 26 degrees left over for S. It's incredibly satisfying how perfectly that all falls into place.
Okay, go ahead and mentally grab your compass and ruler. It is time for geometrical constructions. Don't stress, this is way simpler than it sounds. We're basically just bringing all these abstract math rules into the physical world through accurate drawing.
Let's say you need to create a perpendicular bisector. That's a line that perfectly chops another straight line right in half at a 90-degree angle. The absolute crucial trick here is keeping your compass width exactly the same the entire time. You just open the compass slightly wider than half your line's length and draw sweeping arcs from both ends of your starting line, points P and Q. Where those arcs cross, those are the exact coordinates for your perfect bisector. Just connect the dots.
And you can use that exact same logic to build angles. A simple sweep of the compass instantly builds a flawless 60-degree angle entirely without a protractor. You just draw a long arc to find a starting point, keep the compass distance strictly identical to strike a crossing arc, and you've geometrically locked in a precise 60-degree spread. It legitimately feels like doing a magic trick right there on the paper.
All right, moving on to Section 2. Angles related to intersecting lines. Let's scale up our toolkit and see what exactly happens when two straight lines cross each other and create a whole new set of relationships.
Whenever lines make an X shape, they create what we call vertically opposite angles, right at their center vertex. The absolute rule to remember here is that the angles directly across from each other are perfect mirrors. They are completely congruent. If the top angle of your X is 40 degrees, the bottom angle is 40 degrees. Guaranteed. Every single time. Then we have adjacent angles. The easiest way to think about adjacent angles is to picture next-door neighbors sharing a wall. They share a common side and a common vertex, but their rooms never, ever overlap. And the golden rule here is that if these two neighbors sit side by side on a perfectly flat straight line together, they will beautifully add up to our magic number of 180 degrees.
Now we're jumping into Section 3, Parallel Lines and Transversals. This is the grand finale of the chapter, where we introduce lines that run side by side and never ever touch.
But parallel lines only get mathematically interesting when they get interrupted. Enter the transversal. This is a massive vocabulary word for your exams. A transversal is just the single straight line that ruthlessly slices right through your parallel lines. And when it does that, it spawns a highly predictable and highly testable series of angles.
You'll want to mentally screenshot this because it summarizes the 3 absolute rules for transversals that you need to know to determine parallel lines. First, corresponding angles. These are the angles sitting in the exact matching corners at each intersection, and they are completely equal. Second, alternate angles. These are located on the inner side, but on opposite sides of your transversal line. They are also exactly equal. And finally, interior angles. These sit inside the parallel lines on the same side of the transversal, and they will always sum to 180 degrees. If all 3 of those conditions are met, your lines are undeniably parallel.
But geometry isn't just about abstract lines on paper. It dictates how we interact with the physical world. Just imagine standing outside a really tall building. Looking up from your normal horizontal eye line to the roof forms what we call an angle of elevation. On the flip side, someone standing up on that roof looking down at you drops their line of sight below the horizontal, which forms an angle of depression. It's the exact same geometry, just from 2 entirely different perspectives.
Let's bring it all home with Section 4, Summary and Exam Tips. We're going to condense all of this theory into a quick, punchy, easy-to-remember toolkit for your exams.
Keep these absolute rules front and center in your mind, and you are going to breeze through whatever angle calculations get thrown your way. Remember your 180-degree straight lines and interior angles, lock in your 90-degree right angles and your full 360-degree whole turns, and never forget that an intersecting X creates perfectly mirrored equal opposite angles. You've totally got this.
Because here's the thing, mathematics is literally everywhere around you. It's in the floorboards beneath your feet and the intersecting beams in your ceiling. So take these tools off the page and test them out in the real world today. Try to spot some parallel lines right in your room, or maybe estimate an angle of elevation to a high shelf. But here's a final thought to leave you with before we wrap up this explainer. If modern architecture and engineering rely completely on the absolute rules of parallel lines and transversals to keep skyscrapers from collapsing, what do you think would happen if a builder was off by just 1 single degree? Keep exploring, keep questioning, and I'll see you in our next explainer.